in this example, we're given a circuit that has two independent sources and one dependent source, and we're being asked to compute V0, which is across a 1 kilo ohm load, using Thevenin. Okay, so I called it load because what I'm being asked to do is to compute the V Thevenin on R Thevenin equivalent of the circuit, okay, without that 1 kilo ohm. Basically, everything in the circuit except that 1 kilo ohm. I'm trying basically to figure out what the Thevenin equivalent for this part of the circuit, and then afterwards, once we're done, what we can do is we can connect that 1 kilo ohm and see how the circuit actually affects it. So that's 1 kilo ohm in here, that's plus, and that's minus, and that's the V0. So our task now is just to figure out what that is. And there's multiple ways to tackle this issue. First, we're going to have to remove that resistor, of course. Okay, and now let's try by figuring out what the V Thevenin is. So the V Thevenin value is the V open circuit in here. It's convenient. It's not V0 anymore. It's V open circuit. Okay, and that's exactly the plus and exactly the negative in here. So how do we do this? Well, there's multiple ways. You can just do loops, KCL, KVL. I'll just basically write some equations in here. And I think what I will do is I'll use nodal because actually maybe mesh. I haven't used mesh before here, but let me just use mesh. Maybe what we do is we say, well, there's a current in here, and that's 2 milliamp, and there's another current in here, which I know. Why am I using mesh? Because I have two current sources, so why not? All right, so I'm going to call this here as I1, and I'm going to call this one here as I2. Okay, so, well, I1 is just simply 2 milliamp. I don't need to write an equation. Well, I2 is also, I don't need to write an equation. It's negative 2Ix. But I don't know the value of Ix. Well, Ix is here. So this is the value of Ix. Well, it's simply, Ix is simply I2. Let me just write that. That's the constraint equation. It's just simply I2 minus I1, which is I2 minus 2. Then we can combine these two together in here. That becomes I2 equals negative 2. I believe I2 minus 2 in here. All right, so we'll do a little bit of algebra, and that will give me 3I2 equals 4, which means that I2 is just simply 4 divided by 3 milliamp. All right, of course I can figure out the value of Ix since I have everything now. I'm just going to write it in here just in case I need it. Ix is just simply I2, which is 4 divided by 3 minus 2, which is equal to negative 2 divided by 3 milliamps. All right, so I think we have everything we need to figure out what we are looking for in the circuit. What we're really looking for in the circuit is the V open circuit in here. So if you think about it, and I'm looking at these, that will be 12 plus whatever voltage drop is across the 1 kilo ohm. So let me just write this in here. So whatever that, it will be 12 plus whatever voltage drop in here, and I'm just going to call it V1, for example. All right, so let me just write that here. So the V open circuit will be 12 plus V1. You can write the KVL and see it, but that's it. But what about V1? Well, V1 is simply the value in here, which is, well, we can use the mesh current or we can use the nodal, the actual current in here. So let's use the mesh current. So based on the mesh current value, it will be 1 times, well, we have a negative in here. So that will be negative, and that will be 1 and times I2, which is 4 divided by 3. So negative 4 divided by 3 volts. That's how much it will be. All right, so now we can combine these two in here, and that will give me the V open circuit is just simply 12 minus 4 divided by 3, and that's equal to 32 divided by 3 volts. And that's about 10.6. Okay, so we have the V Thevenin. V Thevenin happened to be 32 divided by 3. Okay, so let me just write that here. So that will be 32 divided by 3 volts. And that's basically the V Thevenin. So we now move on to figuring out what the R Thevenin is, now that we know what V Thevenin is. So I'll put a copy of this circuit in here. So here, well, we have a dependent source, which tells me that you cannot use the method 1 because I can't turn it off. So I have to use method 2 or 3. Okay, so let me just remove this here before I forget. All right, so which means that it tells me that method 2 or 3, I'm going to use method 2, that I have to connect these two in here, and I need to figure out what the I short circuit is in here. And again, it's up to you the way, the method you analyze this particular circuit. For example, I can use mesh if you wanted to. Let's call this I1. We're going to call this as I2, and that will be, actually this is I short circuit, the one I'm looking for. You can of course use nodal as well. It's up to you. I think because we have all these current sources, it might be just simpler to use the mesh current. All right, so let me just write a few equations in here. I believe I1 is not 2 milliamp anymore, because it's actually that 2 milliamp affects the I short circuit and the I1. Okay, so now what we need to do is we need to figure out well, I1 minus I short circuit is just simply 2 milliamp. All right, and then we do the same thing for this particular source in here, or this particular resistance in here. So that tells me, or this particular current source. So 2ix is just simply I short circuit minus I2. Okay, but now this one is in terms of Ix, so I have to rewrite it in terms of the mesh current. So I know that Ix is simply I2 minus I1. Okay, so we can combine these two in here so that I get rid of the Ix, so that becomes 2 times I2 minus I1 equals I short circuit minus I2. Okay, so let me just highlight the equations we have. We have this one equation, this is another equation, and I think we need a third equation in order for us to solve all three different ones. So the third equations, we will get it from, I believe, the I short circuit. Well, the only super mesh, let me just explain. So what we would do is we will use, well, this will be a super mesh because this, like the meshes are actually sharing a lot of current sources, so that will be the big mesh that we'll be using. So let me explain. So we'll be removing this here because we're going to be using it as a super mesh. We'll be removing this guy in here, will be a super mesh. So technically this is also removed. So that leaves us with this big mesh that I highlighted in pink in here. All right, so let me write the equation for that particular huge super mesh. It's actually super mesh. Okay, so we're going to start from here. Okay, so that will become 12 and plus, I believe it will be I2 times 1. And that should be 0, I believe, because there's nothing else. So there's 12, there's the I2 elements, and there are no other elements, and that's it. So that is basically the third equation that we need to solve these equations. So let me just solve them and come back with the answers. So after computing the results of solving the circuit, or solving the equations, this is what I came up with. So that's the number we're interested in, which is I short circuit, which is the same as I Norton. So what this gives us is the R Thevenin. So R Thevenin will be simply V open circuit divided by I short circuit. Okay, and V open circuit, it happened to be 32 divided by 3. Okay, so let me just write that here. That will be 32 divided by 3. And that I short circuit is also 32 divided by 3, and that gives us 1 kilo ohms. And that's basically the R Thevenin. So now we know the complete Thevenin equivalent. So let me just take this here. So the complete Thevenin equivalent to the voltage is 32 divided by 3, and the R Thevenin happened to be 1 kilo ohms. So let me just do this here. That's it. Okay, so this one here is just simply 1 kilo ohms. Okay, that means the V naught that we're looking for, we can use voltage division to compute it. 32 divided by 3 times 1 divided by 1 plus 1, and that equals to 16 divided by 3 volts.